Hello. So in this session, we'll be discussing some basics that we normally need along with openFoam when we work with Linux. Specifically speaking, Ubuntu 20.04 LTS in this case. So in the class, some of the doubts were as to how to navigate the directories, what are the directories, and some of the so that you get comfortable with the file structure. So to address that, let's open the things in parallel first. File Explorer. Okay. So here, when we install Linux, no, this is the folder, this is the new directory, or you can say new disk drive that is created. So let's go in. This is Ubuntu 20.04, and let's go to home, Kunal. Then it will be your name in case you have installed it correctly. Then open form, then this, and these are the two tutorials that we have copied from the reference tutorials. Now what we will be doing is we have to navigate to this run directory. Okay. So normally what we write is we go to, let's say, change directory. So it is cd. Yeah. Cd meaning change the directory. Okay. And ls meaning listing the contents. Just listing down the contents. So let's say if we write ls, there is one folder known as openFoam, meaning we are in home. So let's go here. So you are in home and then Kunal, meaning your name, and then you are here. So this is the openFoam. Let's go to change the directory to openFoam. Now we are going inside the openFoam. Then cd Kunal. So we are inside this thing. Then cd run. So inside run. Then let's say we list down the contents again. So it is cavity and bit secret. So cd cavity. Now we have gone inside the cavity. And now if you want to run, so I don't know the solver, but then it may be this open form kind of thing, right? It is showing something. So okay, let's identify the solver. So from where do you get the solver from? It is from the control dict. It is openFoam. Okay. So what you need to do is initially you need to do block mesh. The creation of the mesh that is normally done, and then as a formality here it is check mesh, meaning the mesh is okay, and then at the end you go for openFoam option. The simulation ran and it ran fairly fast, and then you should have some couple of folders here. Okay. After running the simulation you get these time folders. So it is at time t is equals to 0 or the iteration equal to 0 if it is a state set solver, or otherwise it is a time if it is a transient solver. And this constant represents the meshing and the constant parameters. So let's go inside. We are having polymesh. This is the meshing part. The transport properties, meaning the properties of the fluid. Okay. So let's open it. What are we having here is this thing. So it is called kinematic viscosity, and the units are meter square per second. Yeah. MLT, meter square per second. So with this, this folder is now complete, and in this you are having boundary faces neighborhood. So these are the technical points. Normally we deal with the boundaries. So let's open with boundary first. Okay. So there is this moving wall. If you have done the gravity tutorial, you must be familiar with these terms. We'll be doing it again if possible. So this moving wall, meaning so this is the box type of geometry, and the top wall is moving with certain velocity. Okay. So that wall is a moving wall. Okay. Now fixed wall. Fixed wall meaning apart from the top boundary wall, we are having the other three boundary walls. Okay. The left side, right side, and the bottom one, the bottom part. All three constitute these fixed walls. After this, we are having the front and back. In general, please remember that openFoam takes into account only 3D meshes. So if you consider as a block, so we are having the front and the back face of the block. So this front and back are set to empty. The moment we set it to empty, the openFoam realizes although the geometry and the mesh are in 3D, I need to solve the simulation in 2D scenario. This is the very important thing. Others are okay. I mean, you can have fixed walls in the type wall, and there are other types also. we will learn eventually as per the demand of the tutorials and the cases. Moving ball is also kind of wall only. So this finishes the explanation for constant folder. Let's go to the zero first before system. So we are having the P meaning pressure file. So let's open it. So in the laminar case, one important thing to know is this pressure is the kinematic pressure. Please compare it with the standard pressure units with the MLT kind of format, and you will come to know that this is unjustifiable for a standard pressure dimension. So it is a kinematic pressure, like kinematic viscosity by density. It is kinematic pressure. Okay, for incompressibles, wherein the density is constant. Now internal field. So it is at the start. Okay, we are at zero, and in the zero folder we are starting with something. Starting with something throughout the mesh. That is the internal field. So we are setting it to be uniform 0. Okay. Now boundary field. Boundary field meaning all the boundaries of the block. Again, front and back, as we have decided, we are solving in 2D. Although the mesh in 3D, mesh and geometry are in 3D, but then we are solving in 2D. That's why we are setting here as empty. For the fixed walls, which are left, right, and bottom, those are zero gradient. Okay. And the moving wall, the top wall is also zero gradient. Okay. So these are all walls are having the zero gradient boundary conditions, meaning at the wall, just at the wall, whenever there is a pressure profile, if you draw it, it should be a zero gradient. There should be no gradient at that point. Now let's go to the velocity. Let's move. So in the velocity, we are having again the standard meter per seconds units, and then internal field we are starting with, let's say, zero velocity at the start, uniform zero, and now at the boundary field, the top wall we need to move with certain velocity, and that is 1 meter per second in the x direction. Okay, so 1 meter per second in the x direction. Y0 and then Z0. So this is the syntax for this. You will definitely be getting the help from the website, or a little bit of surf should get you here. And at the walls, we are having no slip boundary condition. This is a very important boundary condition because the fluid element that is immediately in the contact with the walls should directly adhere to the stagnancy of the wall, right? Meaning if the wall is stagnant, then immediate fluid element should not just slip through it, and that's why the name is no slip. Okay. The next thing is front and back. Again, the front and back we don't want to solve in the front and back type of case. Front and back type of faces in our cubicle block, and so it is set here as type empty. Next thing, coming out of the zero folder and then going in the system. Okay. In the system, we are having block mesh dict. So by default, openFoam uses block mesh as a meshing utility. We are using GMSH, and that's why this is not at all applicable to us for this case. Control dict is important. Let's navigate through control dict using Notepad maybe. So standard syntax version 7, name control dict and location system. Application we are using icofoam. Please go and read about icofoam. What is it? Transient solver or steady state solver, compressible, incompressible. So there is a list of solvers. Okay, depending on your use case, you can have those solvers available, and these are standards. Advanced users also have learned a lot about this, and they are even trained themselves to code these solvers according to them. That's a different story at all. For the basic use case, we will be using the inbuilt solvers. So this is the start time. So from where to start? So start with the start time. We have defined this, and what is the start time? It is 0, and when it is 0, we are having 0 as a folder. This is really important. Okay. So we are having 0 as a folder, and we need to start from here. This is what is signified from this entry. Now stop at where to stop? At the end time. What is the end time? It is 0.5. So the simulation has stopped at 0.5. What is the delta t? The time step to be taken from 0 to 0.5. It is 0.005. Meaning around 100 iteration must have took place. Okay. Next thing is write control or time step. In which iterations you want to write your simulation entries. Okay. So write interval is 20, meaning the total simulation that we have just calculated were 0 to 0.5 with the interval of 0.005 are 100, and we are writing in the interval of 20, and that's why we'll be having total 5 entries. So these 1, 2, 3, 4, 5. Yeah, because writing in the interval of 20 and total are 100. So 1, 2, 3, 4, and 5. 20 plus 20 plus 20 plus 20 plus 20. Purge write is kind of, before the iterations, when you start to write and you are having some memory constraints. Let's say you are running a very very big simulation, and then you are having some memory constraints. You start with 0, 1, 2, 3, let's say up to 5,000 or something, but then you are interested in the end result, or let's say end last two results. So you can set purge rate accordingly. Purge rate meaning you will be containing the last two or three folders you want, and before that everything will be removed in the real time, in the real time of the simulation. This is the very important function and will be used whenever there is a memory constraint. In general, there is no need. Write format ASCII, the standard format. This write precision is again important. So write precision 6, meaning it is considering 6 decimals after the point for any value for any variable, in general. So we are having the precision of 6 digits after the decimal. Write compression of time format general precision is 6, similar for the this thing, and runtime modifiable true. This entry is important because the simulation is running and you want to modify the time step. What is the time step? So this is the delta t. Now if you want to modify this while running the simulation, you can do that if this option is kept true. So if this is false, then you have no control over the time step. The simulation will finish by the default time step at the input you have supplied as this. But the simulation becomes stable sometimes in the near future, and then you decide that okay, it is comfortable for me to increase the time step so that I converge faster. So accordingly you can do it in the runtime. In the I mean the simulation is running and then you are modifying the time, so that provision is also there again for the advanced user. But just to summarize the key entries that we are studying right now. So I think that summarizes this cavity tutorial, and mainly the structure stays same. In zero you will find pressure, velocities, or this structure is for the laminar cases. For the turbulence it turns out to be you are having the k, you are having epsilon, and other files to start with depending on the simulation case you are having. In the constant you will be compulsorily be having the meshing part, right, and the constant part, fluid property part you will be having. In the system, let's ignore block mesh dict. You will be having control dict as an important thing. FV schemes and FV solution are, FV solution mainly deals with the criteria. Okay, criteria as to where the simulation is assumed to be converged. Okay, when control over the residuals, control over the different parameters, it is set by the FV solution. FV scheme, which kind of scheme, meaning you may go for so just as a similarity, you can integrate using standard integration, or you are having some numerical methods. Let's say trapezoidal rule, Simpson's rule, one third rule, 3/8 rule, and whatnot. So which kind of integrator you want to use in that case? So similarly, there have been complex differential equations that are employed in the openFoam, and accordingly the schemes are defined. Let's open it. It may look little horrible at first. So this time dependent schemes are Euler, and then pressure is Gauss linear, this U is Gauss linear. So please don't worry about it again for the advanced users. But then just to introduce, this is all it is. This is FE solution. FE solution is having the control over tolerance and relative tolerance. Tolerance meaning the alternate the nth entry and n minus 1th entry are difference. Relative tolerance meaning you are having the ratio of the nth of the n minus 1th term and divided by nth term. So this is the relative tolerance. So the simulation will stop whenever the p converges. So for p it is okay. If u is not converging, then this is the criteria. If both are converging, then only the simulation will stop. Otherwise, the solver will stop the function for p. If the criteria for p is satisfied, then it will solve for you. Eventually, your computational resources are balanced along with your accuracy. So all of the ticks are here only, and this is piezo algorithm. We'll discuss about it later. So it this it acts as the communication between your mesh and your simulation configuration. What kind of mesh you are having, and how would you like to modify it as per your simulation data. So this was all a basic file structure of the any openFOAM case in general. So navigating through this directory again, ls, then cd, let's go to 0, then coming out cd space dot dot, you have come out. Many of the things are achieved by these 3 4 commands only. If you want to go to text editor, you can use nano. Let's use gedit. It is working perfectly for my case, so I will go for gedit. Okay, because 0 is the folder, it will not open. So what we need to do is gedit 0, and let's open u, because u is the file. Gedit is a text editor. It will open text file. It should have opened. Okay, I don't have gedit installed in my system. Let's install now. Sudo apt gedit. Sudo apt install. Please install. So similarly, you can use other text editors like Vim or Nano or gedit. So these are some simple shortcuts that you can have, and accordingly you can. So it is getting installed in the background. So what we'll do is we'll go here and we start a new terminal, then going to run, then cd. This is also very important shortcut. You don't need to start with scratch again. Just write run and then you are there. Cd cavity, then ls, then let's say you type in parafoam. So does that open? Yes, it opens up, and then you click on apply. You are having this thing here. What you want to see, I need to see the velocity, and now I am running the results. So at the end time of 0.5, our simulation finished at 0.5 seconds. Now clicking on it, we have got this such type of velocity profile. Right. So this is what our result shows. For the pressure, something like this. The magnitude should be similar. I mean 4.8 and minus 4.4, something like that. That depends on the the difference depends on the grid. So at some point there is high and some point there is slight difference. So this is all about this thing. I hope the gedit must have got installed. No, still running. Speed is low. Okay, let's not bother about that. We can anyway open everything in gedit. Sorry, notepad we are having. So let's select notepad and like this. This is the kinematic viscosity as I have discussed. Apart from that, I wanted to cover something really important. Yeah, so this was it. So what I did is I just made a screenshot kind of thing from the video so that we can fasten things up a little bit. So it goes something like this. You will use terminal post processor and everything. Okay, these are the prerequisites, and then lead driven cavity, the tutorial we have already done. So this is the velocity, and this is the point one is the height, the cavity, and this constitutes the cavity. The top is the moving wall, and the three are the fixed walls. Make a directory foam run. This we have already done, and that's why we are able to navigate to run directory. Let's go to run directory directly. Something like this. I've been repeating it again because this is a very good shortcut in my opinion. You don't need to write dash the foam run or something. CD foam run. So we are kind of making the thing simple. Now this is a very important command. So you run it where you want to copy the files. So let's say I want to copy the file. I need to open a new session. Okay. Now then I want to go to run. Then I want to copy file in this run directory from what? From cp minus r. It is a recursive copy. Now this is important. Dollar home underscore tutorials. So I want to copy from tutorials, then incompressible, then icofoam. So I am pressing tab to make it autocomplete. Okay, so there is a mistake, I think. It says incomfoam tutorials incompressible. I'll just remove this. This was not there initially. Why is it come out? Then I will go with the icofoam to detect. Yes, I'm good to go. And then cavity. I think this thing is making issues. Suddenly it is coming in and then bothering. Okay. Open foam. Then cavity. Let's say again cavity space dot. The cavity should be copied, right? Although we have run some kind of simulation, we should be able to see that you know it. I don't know if it is copied or not. So let's copy some other tutorial, right? Let's remove the cavity wala part. I'll just remove it. That way we can verify whether it is copied or not. So let's run. Let's remove cavity tutorial. It should have got removed. Unspecified error it says. Okay. Unable to delete. Let's go here. Remove all the commands. Then rm minus rf. It is called cavity. Minus rf. Do I need to close this? Something is happening. Go into Linux, this thing, foam, this, openFoam, this. Okay, so that is already removed. Nice. Good now. Then again try this command cp minus r wala. So it says cp minus r foam tutorials. Just try copying this thing. Something bad has happened. cp minus r, this thing, cavity and cavity. There is no error, so I think it should be here. Let's press F5 and there you are with the cavity folder. So the command is working. So this command, rm minus rf that we have just used to delete the cavity folder. So it is rm minus rf and then the folder name cavity. Additionally, what are we having in our pocket today is this is the formula for the kinematic viscosity, and in this tutorial they have set u as 1 meter per second that we have seen in this. Where was that? This one. Go to cavity, then 0, then u. The one should be. This is the one. Okay, 1 meter per second that they have set. Further, the characteristic length d is 0.1. So this is the meshing part. Let's not worry about this currently. So it is set in inside the block mesh. End result is this, and then at the end we have learned how to open the terminal and everything. Yeah. What is the status of gedit? Taking a lot of time. Let's forget about it. So I think that's all for today's tutorial. So it is tutorial 1 that we have seen of the cavity tutorial. We'll be having further tips and tricks discussed in between as to what are all the difficulties we might face. So thank you so much for your patience listening. Let's meet in the next tutorial. Thanks.